Okay, so tangents and the derivative. So our first lesson on our beginning of calculus. Now, let's set up the scene. A bottle of water was taken out of a fridge on a hot day where the air temperature was 40 degrees Celsius. Over the course of the day, the bottle will warm up to the temperature of the room it is in. So this is what I've got graphed here, okay? So if you can notice that we've got a lot of red lines, but we also have this black line, and the black line is what we're focusing on at the moment. So it starts off, okay, and it gets warmer and warmer and warmer, but the rate at which this bottle warms up decreases as time goes on. Because if you think about it, okay, there's only a certain point, when this bottle can, or to what this bottle can warm up to, okay? So it can never actually be warmer than the room itself, okay? So it can't be warmer than what it's inside. And, something that starts off pretty cold, okay? It doesn't take very much for it to warm up, but then to maintain that warmth, okay? To maintain that warmth, it's quite hard. So what we're going to do is we're going to look at individually some specific parts. So the water temperature was originally 0 degrees, so it came out of the fridge and it was 0 degrees. And 20 minutes later, it was 20 degrees Celsius, okay? So we can have a look on this graph. Okay, so at 0, it's 0, and at 20, okay, at the 20 degrees here, it's 20 degrees Celsius. Okay, makes sense. So what is the rate that it's rising at? Well, it has an average rate, so it's the average rate of, let's say, average rate of temperature rising, and it's equal to 1 degree per minute, okay? It's going up on an average of 1 degree Celsius per minute. We can see that it's not exactly uniform across the whole minute, across the whole 20 minutes, because if it was, it'd be a straight line, okay? But let's keep going. In the next 20 minutes, so from 20 to 40, okay, so here's my 40 minute one here. But this time it only increases by 10 degrees Celsius, okay? So the average rate, okay, of temperature between this one, so between the 20 and the 40 minutes, is equal to, now this one's only 0.5 degrees per minute, or 1 degree for every 2 minutes. Okay, now if we continue on the third one, okay, so from here to here, it's only a 5 degrees change. Okay, and then in the next 20 minutes, it's even shorter. Okay, but we don't typically care too much about what the average rate is. What we're more concerned about is what is happening at a specific point in time. So to measure the exact rate at which the bottle is heating up, we can look at the gradient of a tangent that is drawn at that point we are after. So let's say we go to that first 20 minutes again, okay? So if we have a look at this first 20 minutes, again, we have this point, or this value A. So the value at which this graph, or the bottle, is increasing at, the rate at the specific point, okay, so at this point, it's going up at a rate that's equivalent to if I was to draw a straight line along here, okay, like this. So the gradient of the tangent, okay, so that gradient, that rise of the tangent, is known as the instantaneous rate of increase at that time x. So basically, whatever this is here, okay, whatever that gradient is of that tangent at A, is what the rate of the water bottle is heating up at that exact moment in time, okay? And as you can see, if we go along here, well, we can kind of see that it's starting to decrease a bit. But, okay, can we stop jumping around, please? Thank you. But we can see that this one is actually, it's not increasing at as much of a rate, okay? And we can see that too, because between those minutes, the value was decreasing, okay? And we can also see that the instantaneous rate at that point there, well, it's actually quite a bit shallower than the one at A. And again, continuing along for C is also shorter. And then again, D, which would keep going, is even, not shorter, is even flatter as well. Okay, and then if we have a look at the start, well, the start, at 0, it's shooting up very quickly until it gets to us, and it's going to, and that tangent that we draw along is going to get flatter and flatter and flatter depending on which point that we pick, going from left to right. Okay, the gradient of the tangent is the instantaneous rate of increase at that time x, and then we can measure those gradients quite easily using graph paper like we've got here, by doing the rise over the run. Okay, so what I'm going to do is I'm going to copy this graph, and I'm going to put another one down here, because the idea is that we can look at the instantaneous rates of change, and we can see what's happening in this situation, in this scenario, okay? And a lot of calculus, a lot of the stuff that we're going to be doing is going to rely on this idea. It's going to be what's happening at specific points in time. Okay, so if I bring that down a little bit, there we go. So, let's start off. Okay, I'm done with you. Let's go. Okay, thank you. All right, so let's look at this more generally. So the gradient of the tangent to the curve y is equal to f of x at any point is called the derivative. Okay, so that instantaneous rate is called the derivative. So let's write that. Instantaneous rate at a point is called the derivative. Okay. So more generally, that's called the derivative, and the gradient of the tangent curve y at x at any point. Okay, so it doesn't matter which point we can pick. It doesn't have to be one of these really nice ones. Like I could pick this point here, or this point here, or this point here, and do a tangent at those points. Okay, and that would still give me a value or a rate, which we call a derivative. Now, the gradient of the tangent is the instantaneous rate of increase at that time x. So measuring the gradients at marked points above, in the above table in this graph here, is going to give a table of values of the derivative. Okay, so we could, sit here and actually count them out. But let's just do this first one. So it's not quite at that value there, but that's my rise, okay? And the run at this point here. So remember, we're doing the red lines now, the tangent. So that's why I'm including this bit up here, okay? And we do the rise over run of that, okay? So for this A1, I go from this part here, and I would go down to, okay, this value here. So the rise is that one, and the run is that one. And these rise and runs, as you can see, they change. We're used to seeing rise and run used on straight lines, okay? But when we use rise and over run on, when we use on straight lines, we could say, it's the same all the time. But as you can see in this case here, it changes over time. It's getting smaller and smaller and smaller. Now, the reason for that is because we can see that it is a curve and it is decreasing in size. And so the derivatives we can write down like this. So x is equal, so x, and we'll put some values in. So we'll go 0, we'll go 20, we'll go 40, and we'll go 60. Okay, so if we were to actually do this properly, we'd get the derivative. So that's what this symbol stands for, and I'll write it up here. So so it's like f of x, but with just a little dash. Okay, is the derivative. So the derivative at these values at 0 is 1.39. Okay, so that is the gradient of the tangent at the point 0 of the curve. At 20, it's 0.69. At 40, it's 0.35. And at 60, it's 0.17. Okay. So just to summarize, that f dash of x that we had before, so the f dash of x is the gradient of the tangent. So is the gradient of the tangent. So if I was basically to make really straight lines that only touched one point on the graph, is the gradient of the tangent to y is equal to f of x. Okay, so if I was to graph the actual function at each point of the curve. Okay, so that's our introduction to calculus and the whole idea behind it. Okay, what we're going to be doing in a moment, or in our next video I should say, is looking at when the gradient function is a linear or constant function, okay? So when the function itself that we're going to find the gradient of is linear or constant.